Next up, we're going to hear from Adam Bacon of AHA. Thank you very much.
Right, can everybody hear me? All right. So just a little introduction. So Adam Bacon I'm a technical sales engineer from AHA. We also go by AHA. It's all good. People in our own corporation, that's what they call us, AHA. And it's a fun name. The only bad thing about that is that all the people looking for American Hospital Association and similar things, they always hit our website. So that's always fun. So today, I want to talk a little bit about, really it's a little bit of a recap of what our keynote speakers yesterday and this morning have talked about, some of the trends in, first in the advances in space technology, some of the things that are making that more accessible, and also the idea that the union, or heterogeneous computing, the idea of this merger between CPUs and FPGAs or other devices, and how that is impacting SDR. It's titled Accelerators in Software-Defined Radio. Particularly then we'll talk about RF knock and our experience with that so far. Also, we have some new blocks for the community to try based on our SATCOM IP. So we'll kind of go from there. So AHA, we're located in Moscow, Idaho. The University of Idaho is located there. We spun out of the University of Idaho back in the late 80s. Our first project, we did the first single chip Reed-Solomon solution for NASA. And since that time, we've been involved in Feck in different kinds of capacities. 2002, we were acquired by Comtech EF Data. They're a satellite modem manufacturer. So we do our group does all of the error correction for them, and a lot of the advanced research for those guys. Just a couple years ago, there was a brand new satellite standard. You probably heard it mentioned a couple times so far. DVB-S2X. It's the latest satellite standard. And with satellite bandwidth being so expensive, or traditionally so expensive, it's important to have optimal Feck, high performance stuff. So that's, in 2014, we came out with a full path solution, so both the Feck, but also then a full modem for the whole, or IP for the whole modem. So AHA stands for Advanced Hardware Accelerators. So anything kind of coding theory, information theory, anything with a Galois field, that's kind of what we do. So, anybody know who this guy is? He doesn't work for us, but Thaddeus has met some of the people that are there at AHA, and some of it's hard to tell. No, so, kind of this first slide here, I'm going to talk about some of the trends with the accessibility for SATCOM, satellite and space, becoming more accessible. So the first point is the idea of commoditized space. If I wasn't using the PDF version, you'd see the SpaceX reusable rocket landing there, both with launch costs decreasing, and as our keynote yesterday, Dr. Paulo was talking about, the ability to launch small payloads, small satellites, CubeSats. They've brought the cost of space, just in the advance of technology as things have miniaturized, but the ability to get them into space has been bringing has been making a lot of things possible that weren't before. As humans, we're kind of wired to explore, I think. You know, why are we pushing out into space? One, I think it's becoming more of a technical reality, but why do we want to go to Mars? Just, I think we're curious. So there's some social forces there, but then that has also created some economic forces that have resulted in a lot of investment. So just probably can't see that figure very well, but in just the last year, last couple of years here, tremendous amount of investment in space. Another factor is we're starting to see these high throughput satellites. Here on the left, you have your kind of traditional setup, and now we're able to get a lot more efficiencies, have spectral reuse, increased capacity, 20 times more than the old ones. For example, the Viasat-1 that launched in 2011, it had more capacity on that one satellite than all of the satellites over North America at that time. The other factor that I wanted to point out is we're seeing, as far as military, a lot of UAV, UAS systems that are using satellite bandwidth. One thing I didn't realize, a colleague pointed out to me that already the DoD, 80% of their SATCOM is over commercial satellites. The amount of bandwidth that is needed is quite significant, and it's expected to continue to grow. The number of UAVs are expected to double in the next 10 years. So the other thing, beyond that space is getting cheaper and more accessible, we're seeing advances in computing, particularly the union of CPUs and GPUs, or CPUs and FPGAs. So, as Dr. Clancy was talking about this morning, the Moore's law is, or what used to be Moore's law has kind of gone stagnant, and we're looking for other ways through parallelism, through other different things to try to increase performance. So one trend that you'll see is that more and more FPGAs are becoming part of that equation. Several, the Xilinx, Altera, having processors coupled with their FPGAs, Intel and Altera, and kind of seeing where that goes. Everybody kind of looking this way for improvements in computing to kind of get to the next level. One thing that I thought was a little ironic, the number one application for FPGAs is in communications, and really in communications by software-defined radio, they haven't really been able to take advantage of that. That's been changing. There's the RF NOC framework that EDIS has developed, and in the last year, it's starting to really come along, and you hear people talking about it a lot this conference. So if the FPGAs can be made more accessible, then that's kind of I think the future of computing. That's kind of a trend that others have noticed. So I want to talk a little bit about the potential of RF NOC, or the FPGAs that are in these radios already. So our first year at GNU Radio was last year, and we presented on, we put a complete DVB-S2X modem inside of an EDIS X310 platform on the Kintex 7410. We didn't use GNU Radio per se, but took over the FPGA. So it was just a straight RTL implementation, but the kind of performance that we're able to get, again, I apologize, the graph is a little small, but the take home is that it's very close to the Shannon limit, very high performance. Especially so when you're power constrained, trying to get to squeeze every last bit of gain out of the Feck. So again, 72 megasymbols per second, over 300 megabits of data transfer. So some very fast processing that's possible in the FPGAs. And just a note, if you look on YouTube, you can see our talk from last year if you want to know more details about what we did with that. That's a little bit of the potential. So just talking a little bit about RF NOC itself, I'm definitely not an expert in this area. I'm a newbie myself. But the basic idea that you have different configurable blocks connecting to a crossbar through, and then connecting, being able to control that from GNU Radio. So looking at the software stack, there's the GNU Radio integration, UHD, which provides the drivers and such to talk to the hardware, and then the actual FPGA that's located there. So this type of accelerator or software stack, driver stack, where you can, let's see. So we also do some other different types of accelerators, and I think they're definitely on the right track here with having some kind of a transparent API, but then still giving access to the bare metal, so that you slide your accelerators right into the software stack, nearly transparent to the user. So this last year, after coming to GNU Radio Conference and learning about RFNOC for the first time, we were curious what kind of things people wanted to accelerate in these blocks. So using the GNU Radio mailing list, we did a survey, try to see, okay, who's interested, what are they interested in. So not scientific at all, but we had 76 respondents, people from government, academics, and industry. And the first thing we wanted to know, or one of the things that we wanted to know, is the priorities, the design priorities for people. So thought this was interesting. So we asked them to rank which one was important, 1, 2, 3. So 1 being the most important, and 3 being the least important. You can see that the most important was performance that they were looking to get. The other one was development time, and cost was the lowest. So again, kind of prototyping, but trying to get more performance than they could just with the software. Again, we asked them what kind of cores they'd be interested in. See, demodulation, modulation, error correction, and some of those other ones there. So that's one of the other things. We put together a word cloud based on the responses that we got. It was a open comment section where people could type in whatever they wanted accelerated. So the larger the image, or the larger the word, the more frequent it showed up. So you can kind of get a feel for some of this. So highlighted here just a few of the ones that we were interested in a little bit more. LDPC, S2X, S2, decoders, different things like that. So after filled out the survey, we felt there was enough interest. We partnered with EDIS, Virginia Tech Hume Center, and AMSAT to provide some RFNOC blocks based on our own IP. So talk a little bit about what we put together and what it is that we want to provide to the community to try out, to play with. Just the thought, what would you do if you could get access to a state-of-the-art Feck? And what if you could get it for free? So this is a block diagram of the inside of the, it has the LDPC Feck encoder. It also has a symbol mapper included. The final version for applications where you don't need the symbol mapper, it's easy to take out. And these are IP blocks instantiated inside, and then some extra interfacing logic to make everything line up. But bytes in, symbols out. So we have a couple status registers, things to reset the core, specifying what coding you want to use, what modulation you want to use. Also, the ability to read back the errors and to some just basic frame checking. So how many frames in, how many frames out. So that's the encoder. I guess the best way to learn something is to try it and just to jump in. So that's, we had Thaddeus from Virginia Tech come out to AHA and kind of help us put this together and test it out. So my goal or my hope was that we'd have a download link for you today. That's unfortunately not the case. That should be forthcoming in just here in a couple weeks. We have some bugs that we still need to work out. I think it's just our unfamiliarity with the NOC framework, and so that's just sometimes a little bit of a process working through that. The second one, so coupled with this block, also we have a Feck decoder and a LLR demapper, so it brings in we calculate the log likelihood ratios, map it back into bits from IQ data, and the Feck decoder, Feck encoder, they support all the DVB-S2X mod cods. They also support very low SNR codes, so which is something that is new for DVB-S2X. So the number of iterations, again, very, very similar structure, but kind of a complementary. So we provide IP. It's one of the things that we do outside of our corporation, but we also wanted to have something. We took one of our evaluation cores, and that's what we're providing to the community for people to try out. You can see 10 megabits data rate, so it's free for anybody to use, and just there is a timeout. So after a certain number of frames, generally it's about an hour at 10 megabits, then the core times out and needs to be reset. So something to kind of get your hands dirty to play with. We're looking for some feedback on, like I said, I'm not an RF NOC expert, so my flow graph is definitely not pushing the boundaries, but I know there are probably some here that have that capability to be able to try and drop that out. And so that's something that we want to provide to the community. Also, we're working with both AMSAT and Virginia Tech Hume Center on their GEO project, and they'll be able to use that on their downlink. So it will get finished. There will be a link. So the way the licensing works, it very much just like if you were to generate Xilinx IP, that IP then just gets stitched in. So the IP is from AHA, and we'll provide that piece. So after last year at GNU Radio Conference, we had a number of people that were interested in trying out the DVB-S2X modem on the X310 platform. And there were some things that we had to do to, particularly in hacking in a UART port through the GPIOs, that made it a little less, for the lab and for prototype, it was just fine. Looking forward to people that wanted to then take that and move it into production. That was something that there's a need there that we saw. So one of the things that we've been working on is a very small form factor. Basically, it's the complete DVB-S2X modem in a small card, 40 megasymbols, 200 megabit data. Also, just other things that we could do and be happy to talk to people about is other IP that we do provide. So different error correction, compression, encryption, different things like that. So I believe that that was the last slide, but yeah, so we'll be providing through the normal channels, so we'll have a link out on the GNU Radio mailing list and other formats to know where you can download the blocks to try them out and see what kind of improvement that kind of level of Feck can make in your designs.
Okay, do we have any questions for Adam? No? All right, well, let's thank our speaker. Thank you, Adam. So if you do have any questions or you want to chat about SATCOM and RF NOC and FPGAs, AHA is in the booth room.